Leah comment causal inference using the G formula and STAN.
Okay, so my name is Leah Comment, obviously. I'm a fourth year PhD student in biostatistics at the Harvard School of Public Health. And I'm going to be talking about causal inference using the G formula and STAN. So just to let you know, everything, the slides, like a nice detailed write-up, all available on my GitHub, and I'm sure they're going to migrate over to the full StanCon GitHub page as well. So all of the STAN files that I show you here are available, and I have a lot more. I have this full write-up about like the motivation and just a little more of the detail that I just absolutely, there's no way I could have time to talk about it today. So in case you haven't ever heard of causal inference, I don't want you to be extremely bored during this talk, so I'm going to give you a little crash course. However, I am going to say that I'm omitting a lot of the rigor, so it's not like all of a sudden I think correlation equals causation. There's a lot that's being left out of this. However, the references on the documents and also for these slides are two really good treatments, plus like this Bayesian G formula paper that I found really helpful. So why did we try to make correlation equal causation? Like, why are we trying to do this thing? And the real answer is because lots of times we can't randomize. We can't get that conclusive evidence. And so we have to make decisions based on observational data. We just don't have another choice. So for policymakers, it's really useful to have targets that we've identified for policy intervention. If we're trying to move some health measure around. We can also use causal inference methods to think about making better projections for what would happen if we implemented some policy. And then, like I said, lots of times we make decisions even when we don't have access to conclusive data. So sometimes the decision not to act is in itself a decision. So we need to be able to make these decisions intelligently and sort of think about them even when we don't have rock solid data sets. So like I said, correlation still is not equal causation. And I'm not going to be very rigorous today, so I apologize for that. So a couple of different schools of thought in causal inference. Today I'm going to be working in the potential outcomes framework. And the potential outcomes, you might have heard them called counterfactuals. And the idea is that we've got some treatment or exposure. I'm going to be just talking about like binary treatments. And so we have some exposure of interest A, and we're interested in some outcome Y. And under some assumptions glossed over greatly here, the potential outcome Y little a, right there, like that little subscript, is the value that Y would take if we were able to intervene and set the variable A to this value little a. So for binary A, you just heard about in the last talk, the average treatment effect. It's like the difference between these potential outcomes. So the way I like to think about it, and the way I've been taught to think about it, is that like everybody walking around has different like values. Think about them as like little cards on their forehead. Like what would happen to this person if they were treated? What would happen to them if they weren't treated? That would be their Y1 and their Y0. And depending on what happens to them, we actually get to observe one of them. So the problem with observational data, and the reason that you've been cautioned against causation a lot, is that we lots of times have all these confounders. So here we've got some treatment assignment mechanism that depends on baseline covariates, and those baseline covariates are also important in determining the outcome. So that's confounding in a nutshell. Oh, and just to make a little point here, I'm saying that this right here is a causal diagram. So I am saying that Z causes people to be assigned to A, and Z causes Y, and A causes Y. So the G formula, developed by Jamie Robbins, who's in the Department of Epidemiology, kind of a genius, actually, I would say. It looks very easy here. This is the simple G formula, but it's basically a standardization formula. And it's a way of saying, like, how do we talk about the means of these distributions for these potential outcomes, or do we call them counterfactuals? When the treated and controlled, treated and control populations look different with respect to their confounder distribution. And so the idea is, if you really nail this outcome model, this Y given A and Z, then you understand how Y is being assigned. Like in the population, you understand this data generating process, and then it's just a matter of standardizing it so those populations look the same with respect to their baseline covariates. So that's the idea behind the G formula. Like you're averaging over some baseline confounder distribution. And that's one of the things that's sometimes like missing when you just look at that E of YA. We don't see that it's actually being averaged over the confounder distribution. So this requires no unmeasured confounding. That's the article of faith that we're taking here. And this is the biggie and like really the reason that you should be careful when you do causal inference, especially with this. So the average treatment effect for moving A from like little a to A star for the whole population would just be this thing that we've defined here. So the usual way that happens is you spend a lot of time, like in the frequent test method, is you're going to spend a lot of time trying to get that outcome model right, that y given A and z, and then you're going to use the empirical distribution for that baseline confounders, and that means that you're using the frequentist bootstrap for all sorts of inferences. So Bayesian version of the G formula, I have not invented this. There's this really great paper, it's in the references, and has, like I'm showing you here, sort of a basic approach, but they have it for longitudinal treatments as well. And the idea is that if you're taking parametric models, which are indexed by parameters theta, the Bayesian G formula is basically like, once you're conditioning on your observed data O, you can think about having like drawn a new person, right? We're trying to make inferences about a new person that we're trying to implement this intervention for, right? So you've got a new set of baseline confounders or covariates, Z, and you need to integrate over that, and you need to integrate over the uncertainty in the parameters. So that's what that P of Y, like that the law of Y tilde A given the observed data. That's actually talking about like the distribution for these potential outcomes. So where things get a little interesting, and I'm not going to go too much into depth here for some of this, but really embedded in these assumptions here is that we're thinking about like if we could set the treatment to this value little a for the whole population, like what does that population look like? If I'm learning about data in one area, like learning about the causal mechanisms in one data set, like, and I want to sort of make projections about a different set of people, I need there to be similarities in the data generating process in the sense that like I need there to be causal transportability. The way that stuff happens, like everything unrelated to the treatment assignment mechanism in the population where I'm learning about the data or learning about the causal process, needs to be the same as in the population where I'm projecting it, right? Like that's the danger of what we're doing. And then in theory, like there's some need to have comparability with respect to underlying confounder distributions. So nothing too special here. Causal inference and STAN. So I really like STAN for this, and this is, we had this like slick STAN thing yesterday where it separates, or like you don't need the actual data blocks, but I think it's a nice thing for here for sort of explaining like where the model fitting happens and where the causal stuff happens. So the idea is there's really two steps. One is you're learning about stuff in your data. You're getting posterior draws of your parameters for all these models that you've built that you're trying to like learn about this data generating process. And then there's the step where you're trying to do causal inference. So you use posterior predictive draws. You're trying to say a new person walks into the clinic. The doctor has to decide whether they're going to give them this new medication or not. And like you're trying to figure out whether it would be a good thing for them to get this new medication. So all of that happens for me in the generated quantities block. Oh, and one thing that I'm not really going over here is that if I think that I really am talking about intervention in a new population, then maybe that confounder distribution shouldn't match the one of the original data set. So like you can imagine from a policy perspective, you know, like I work in cancer health disparities, I'm looking to see like cancer staging. We can never go back in time and get people to have gotten colonoscopies 5 years ago. Like that, maybe it would have made a difference for them, but that's just like not the population I'm working on anymore. The population I'm working on, if they're American, they're more obese than they were 5 years ago, or things like that. So like we might have a different distribution of confounders that we need to deal with. So here's this really simple observational data example. We're not assuming anything in particular about the distribution of Z, although in my notebooks they're binary. And then we have a binary treatment A, it's easier to think about it, and then I'm just using a binary outcome Y. So we're going to say that Y is being generated according to the logistic model. And this is where we're making some strong statements about like, this is the data generating process. Oh, and I just want to point out that the fact that this is a logistic regression model means we have non-collapsibility. And we also have non-linearities in the treatment effects. Because if we have different baseline confounders, then they had like different odds under, or they have different odds of the outcome under treatment versus control. So, all right. So I have the code online, but I just want to highlight the important parts of this thing. So this part right here looks a lot like any other regression model. And the only thing that I've done differently, and I would recommend this if you're trying to do causal inference in STAN, is to separate out stuff that's static. For me, that would be like the intercept and anything related to disease. So that's my design matrix. It excludes the observed treatment. And then I just have the observed treatment as in a second thing. And the reason for that is it makes it easier to sort of think about like how you're going to actually generate these quantities. I do some like classical bootstrapping for the confounders, so I need to have this transform data thing because I don't want to make this little vector over and over. So now we're just doing basic regression, right? We've got a vector of regression coefficients in our outcome model. I already showed you the outcome model. And I'm just separating it, the stuff that has to do with the baseline confounders and the stuff that has to do with the treatment. So alpha A would be related to like that causal odds ratio. I'm using sort of weakly informative priors. All I'm saying here is that I don't expect like outrageous odds ratios. I don't think that they're going to be like odds ratios bigger than 5 or something. And I'm also saying for the same thing for the intercept, which is that I'm saying that this isn't like a wildly rare or like an extremely common outcome. So I'm just doing the likelihood. So, all right, generated quantities. This is where the magic happens. So think about like from the perspective of you're trying to make inferences about this new population. Here I'm going to show you like what happens if you wanted to make inferences about a new population that looked a lot like your old population in terms of the confounder distribution. But it doesn't have to be that way. So the idea is we want to calculate the average treatment effect in this bootstrap sample. And so what we're doing is we're sort of sampling a row from the design matrix, and then we're basically saying, okay, if somebody came into the clinic with this set of baseline confounders, like what would logical values of the potential outcomes look like for somebody that had that thing? So we're just taking the data generating process to its logical conclusion. You believe this is the right outcome model, then you can come up with the actual things for a given confounder vector. And so here I'm just like I'm adding it together so that we get an average population level treatment effect. So the real stuff that's happening here, it's not too exciting in the point exposure case, but we just want to take this like the mean of the counterfactuals if we gave nobody treatment and if we gave everybody treatment. With the difference of those two counterfactual means. And the idea is that like if you have different segments of the population, then they show up in different blends. And so for here, when we had nonlinearity and the effects, and there's like, basically it means that there's some interaction on at least some scale, certainly on a different scale. What that means is that we're like mushing those all together, right? And the actual population, it's going to be a blend of all of these people's individual level treatment effects. So on average, the thing is that the bootstrapped data set, of course, is going to look a lot like the data set that you pulled those bootstraps from. So switching gears a little bit, I'm going to talk about a slightly more in-depth example, which is mediation analysis. So if you're not familiar with the mediation analysis, think about it as like the natural extension of you had this treatment, you were interested in it, and you're thinking about like manipulating this treatment or not. And maybe you like actually care how it works, right? So like imagine like elongating this thing. Now all of a sudden you have this idea of like how this treatment has its effects enacted. So really we're trying to learn about like the causal mechanisms. So for every causal intermediate, like every way that A is having its effect on Y, we could decompose the effect, like the overall effect, its total effect, into the part that happens through M and the part that doesn't happen through M. Which just seems like such an obvious thing to say, but those have names. Those are natural indirect and natural direct effects. And so if you think about it from the perspective of a policymaker, your boss has come in to tell you, we really need to work on this health disparities thing, and we need to prevent this thing. You want to sort of think about like, how do I prioritize the different ways that people being exposed to something is leading to them getting a disease. So those sort of like, if you think about all of the target mediators, those are the things you could actually intervene on, maybe with an intervention of some kind, and then you could target the paths with the biggest impact. So again, not assuming anything in particular about the distribution of z, everything binary, just to make it easy. The only thing special here is we're adding a model for m, and we're adding m to the y model. Okay, so the actual code here, again, using really vague priors, which I'm passing in through the data block, and then the models have likelihoods for both m and y. Okay, so the calculation of the natural direct effect, let's say that's what I'm interested in, is done in the generated quantities block. And really, this is where you start to see that it's not quite as basic as you might have guessed from the point exposure case, which is that now we've got that whole causal diagram. Think about it, it's got, m is in the middle between a and y, and you've intervened upon a. And now you're just taking that causal diagram and your model parameters, your posterior draws, you're just taking it to its logical conclusion. What does that mean would happen if we gave people the value that they would have gotten under no exposure, something like that. So the natural direct effect, we're looking at these counterfactuals the YA1 and A0. So the mediator value that they would have under no exposure, but they are exposed. So A1, but also A0 in terms of determining the M value. So the part where this gets really interesting and we get to be proud of ourselves for being Bayesian is that this makes data integration for unmeasured confounding really nice. So like I said, we're making decisions with not all of the information. There's nothing we can do about that in some ways. We have to make decisions based on whatever's available. And we rarely have the ideal data set for that. And that means that we're missing important confounders. I work in cancer registry data. We wish we could go back and tell them to add a couple more things to ask about, but we can't do that. And so that's really problematic for causal inference because we need that no measured confounding. And the other problem is that when you're trying to make projections about what a policy would do, it's hard to incorporate that uncertainty that comes from missing key confounders. But yay, prior information comes to our rescue. So all is not lost. We have some information. If you're concerned about unmeasured confounding, that concern comes from somewhere. And so usually that comes from the fact that we've seen in other data sources or other things that there could be this important unmeasured confounder. And so the good thing is that if we email our collaborators really nicely and ask them to fit a couple models in their data set where they have it measured, we can do some sort of data-driven sensitivity analysis. And that's what I'm going to show here. So we're getting informative priors from some other data source that are going to help us to figure out how much our uncertainty needs to increase because we're missing this key unmeasured confounder. So now we're sort of in the same setting except we're worried about this unmeasured confounder U. So I'm going to assume it's binary here. So assume the following generator models. So you've got a logistic model for U, and U shows up in the M and Y models as well. That's where we're getting these troubles from. So if the full data likelihood, if we didn't have U unmeasured, so if we had access to all this data, it would be just the joint product of all these things. And you can imagine sort of, from here you can see, now I'm talking about 3 variables. You could see how this would get a lot more complicated if you had many, many more things, like longitudinal data where it evolves over time. But fortunately, because we picked U to be binary, it's pretty easy to marginalize over it. And I have not developed a method where we can extract information from nothing. So these parameters, everything about U is unidentifiable in the data where we don't have U, of course, right? There's no magic here. However, if you ask your collaborators nicely, they could maybe fit maximum likelihood models in this supplemental or this external data source and send you just the point estimates and the variance covariance matrices. So there are other ways to do data integration, which I address a little more in the document. But for me, what I like about this is that there's no data use agreement, there's no problems with data privacy. I'm just asking for a simple model fit, which is a lot easier to get over that hurdle rather than saying, please send me your data. That's not as popular in medical settings. So the code, like I said, it's available. But really the big thing here is that the likelihood is just a mixture of...
Big dark room timer. Just
okay. Okay. All right. So it's just a mixture of these two things. So it's what it would be if you were 0, what it would be if you were 1. And of course, these probabilities depend on the baseline covariates. And that's just a numerically stable way to do that. So this is the prior information, and this is how you'd actually go about recreating that whole data generating process. So just in summary, the Bayesian G formula is pretty awesome. Big fan of it, and the generated quantities block is really useful for causal inference. And using this data integration thing, the prior information is just a much easier way to do a data-driven sensitivity analysis, and just like sort of naturally comes about through the Bayesian framework.
One question. Anybody?
Very cool. Quick question. First time I hear about the G formula, but it sounds a little bit like matching. Are you familiar with matching? Can you talk about how this is different and better, I guess?
Right. So there's some ways. So the idea that behind the G formula is that Jamie Robbins explains this much better, and I would actually recommend Tyler Vanderbilt's textbook. It has a good treatment of it. But the idea is that you're able to create sort of this, they call them pseudo-populations, where it's basically like you're creating like a population of people where things are comparable with respect to, like, so you're making like, okay, I'm going to imagine that everybody's treated or nobody's treated, and you're just trying to make those things comparable. So I don't know if that totally addresses your question.
I can ask you. Thank you.